Okay, this video is going to be for infinite series unit, and this is for the integral test and p-series. So we're going to introduce two additional um, tests that you can use to determine if infinite series are converging or not. We'll go over the integral test first, and then the p-series test. The integral test, much about this unit is just whether or not a series converges, and if so, to what sum. In one of the previous units, we talked about geometric series, and that's really the only series where we can not only determine by the test if something converges, but if it does converge, we can determine the sum that it converges to. That's very rare, right? In our case, we're talking about for most of these tests, determining whether or not the series converges. All right, so let's get right into it. We're going to expand our list of recognizable series. So far, the only other series we've seen geometric series, which converges when the common ratio is less than 1. And we've seen the nth term test for divergence, which can be used just to show that a series diverges, but it can't be used to show that a series converges. So the integral test states this: if you replace the generating rule, so whatever the rule of the series is, if you write that as a function, it's technically a function of n, which is the index, although typically we just go ahead and switch to using the letter. If that function that represents that generating rule is positive, meaning all the terms in the series are positive, continuous, and decreasing for all of the x's, which would be the indexes, n equals 1, 2, 3, then the series and the improper integral from 1 to infinity of that generating rule either both diverge or both converge. And then there's a caveat that isn't necessarily clear from this. It doesn't necessarily have to start with the first term. If you have a series where you have an A1 term and an A2 term, and an A3 term, and so on, and this is an infinite series, and maybe some of these rules aren't true until, let's say, you get to the third term, and then they stay true after that. It's okay to start this at a different sum. So you can say, well, we've got these first two terms, like A1 plus A2 plus the rest of the series starting at 3, and then you would evaluate this integral from 3 to infinity. Because as long as eventually this converges, you can just add on any number of finite terms. That'll become clear when we do more examples here. Now, here's the thing. This only applies when you have a series which has positive terms and the terms are decreasing. So a lot of these tests that we're going to talk about, they have various limitations, which is why we have to have a lot of them so that we can cover as many series as possible. And then another important note: if the integral and the series converge, the series does not necessarily converge to the same value as the integral is converging to. We're just testing to see if the integral or if the series converges at all. Okay, so there is a proof here of this, and I'm not going to go through the proof. I'll leave it here on the screen. You can take a screenshot or pause the video and read through it if you like, but we're going to get right into using the theorem. So whenever we have a theorem like this, we have to show that the conditions for the theorem are met, and then we can apply the theorem. So the integral test has 3 conditions, right? We have to show that the function for the generating rule results in positive terms, is continuous, and is decreasing. And then once that's true, then we can use the theorem. All right, so here's how we would go about using this, and I'll show you how we want your work to look so that you can do well on the AP test. Use the integral test to determine if this series converges or diverges. All right, so we've got this generating rule. What we're going to do is we're going to write a function that is equivalent to that, and I'll switch to using x just so it's more comfortable when we do the integral part. It's just x over x squared plus 1. And then we have to assert that, number 1, that f is positive, right? It's positive, and that's true. Because this bottom term is squared plus 1, that's always positive, and the numerator will be positive as long as we start at 1 and go on there. So we just assert that that's true, or you can say is positive if you prefer, that's fine. Probably more people do it that way. And you're asserting that that is true. You also have to have that f is continuous, and that is also true. I usually like to do this. F is positive for x greater than or equal to 1, and f is continuous for x is greater than or equal to 1. That way it makes me think about, is this only true after a certain point? And that's definitely true because this is a continuous function. There's no place where this is undefined. Okay, the trickier one is showing that this is decreasing. Is that true? Okay, so to test that, what we typically do is we consider the derivative, right? The derivative is a great way to show that it's decreasing, because if the derivative is negative, then we know the function's terms are decreasing. So we'll compute the derivative of this function, in this case with the quotient rule, x for low d high minus high d low over low squared, x squared plus 1 squared. That simplifies to x squared plus 1 minus 2x squared over x squared plus 1, the quantity squared, which would be negative x squared plus 1 over x squared plus 1 squared. And that will be less than 0. That will be negative as long as this x is larger than 1. Right? At 1, this is equal to 0. So what we can say is this is decreasing, f is decreasing for x greater than or equal to 2. It starts at the second term, that starts to be true. All right, so that means that the integral test applies. Okay, so if the integral test applies, then we kind of start the problem over again. I'll switch colors here. And now we're going to use the test. Okay, so to use the test, we compute the improper integral from wherever this starts to be true, which is at 2, to infinity of, and now I'm going to use the terminology x instead. And then we have to evaluate this integral, which means we immediately have to make this a proper integral, limit as b approaches infinity from 2 to b of x over x squared plus 1 dx. This will be solvable with a u substitution, right? We can make the u the denominator, x squared plus 1. The derivative would be 2x. du is 2x times dx, which means in terms of, I'm just going to do I'm going to ignore the limits for a second and do on some side work over here. This is the integral of x over x squared plus 1 without the limits can be changed to 1 over u, and then this x dx here is replaced with 1/2 du. And so the antiderivative of that is natural log, so 1/2 of natural log of u. And then I like to go all the way back to the original variable x here, because when we substitute with limits, it's harder to try to translate that across the change from x to u. So now this is equivalent to the limit as b approaches infinity of this antiderivative of this, which is 1/2 natural log of x squared plus 1, evaluated from 2 to b. So that means we have to have two copies. We have, let's see, this first one is going to need a limit as b approaches infinity of 1/2 natural log of b squared plus 1, and then another copy minus 1/2 natural log of, this time I'm going to put a 2 in for that x plus 1. All right, so this converges to a number, right? That's a number of some kind. The real question is, what happens over here? Does that converge to a number? If so, the integral converges, and therefore the series converges. If it doesn't converge to a number, then the integral diverges, and therefore the series diverges. So here, what we're doing is, imagine plugging a large number in for b, right? The natural log curve looks like this. So as the input gets larger, the output does go off to an infinity. The natural log of some infinity is an infinity, so this term becomes infinity, right? Therefore, we would say the integral diverges. And then let's go ahead and finish the test. So there we can say, therefore, the series n equals 1 to infinity n over n squared plus 1 also diverges. And then I say the name of the test too, by the integral test. Okay, so wow, that's a lot of writing, right? And as a result, I would say the integral test is my least favorite. test, and I put it on the bottom of the list, and I only do this test if I absolutely have to. It's necessary for some series, but we're going to learn a bunch of other tests. Many of them are easier and less writing than this, so this is sort of the last resort to use the integral test. But sometimes we need it, and this is the right way to format it. Okay, let's look at a couple more examples here, just to get an idea. That one diverged. So let's take a look at this one. We'll have to go through the same process. So first we have to establish the conditions. So we'll write a function for this. Generating rule, 1 over x squared plus 1. And let's see. We have to be able to assert that that is positive, and that is true for x is greater than or equal to 1. That's true. F is continuous for x is greater than or equal to 1, also true. And for decreasing, we'll use the derivative. So I'm just going to go ahead and do the quotient rule here, even though we really don't technically need to. We can move this up, but just to keep it consistent, x squared plus 1, that's low d high, which is 0, so that term goes away, minus high d low, which is 2x, over low squared. So that simplifies to negative 2x over x squared plus 1 squared, which will be negative. The bottom is always positive, and the top will always be negative. So negative divided by positive is a negative, and that's true for all x's starting even at 1. So I could now say f is decreasing for x is greater than or equal to 1. Therefore, the integral test applies. Sorry, the writing is not super great here. I'm using a little tablet here at home. Integral test applies, and therefore we'll go up here and actually do the test. So the test is we're going to make an integral from 1 to infinity of that same generating rule, 1 over x squared plus 1 dx, right? And that we're going to rewrite that as a proper integral. Limit as b approaches infinity of 1 to b of 1 over x squared plus 1. And then that is the arctangent form. So that means that we can go straight to the antiderivative. The antiderivative of that is 1 over 1 times arctangent of x over 1. So arctangent of x, that's the antiderivative from 1 to b. And so that means we're going to have to take our two copies, limit as b approaches infinity, arctangent of b, and then minus another copy arctangent, but with a 1 plugged in. Okay, so we have to evaluate this arctangent thing. So that means the angle whose tangent is something. So if I'm plugging in well, let's do this one first. What's the arctangent of 1? So that means we want to know what angle is the arctangent of 1. Right? That means if you took the tangent of both sides, the tangent of that angle would have to be 1. And on a unit circle, where is the tangent 1? Right there at pi over 4. So this produces a number, pi over 4. Right? And here we're talking about the arctangent of basically an infinity. Right? So if theta has to be the arctangent that produces infinity, then that means the tangent of theta has to be infinity for some angle. And since the tangent is the sine over the cosine, over here, the tangent is, since this is the point 1, 0, tangent 0 over 1, so that's 0. Right here, this is square root of 2 over 2, square root of 2 over 2. That tangent is 1. That's why we got pi over 4. But this point up here is the point 0, 1, where if I took sine divided by cosine, I would be dividing by 0 and going off to infinity. So actually, this angle right here that produces infinity as the output is pi over 2. And that means that this is converging. The integral is converging. The integral converges to pi over 2. And therefore, we can say the series n equals 1 to infinity of 1 over n squared plus 1 also converges by the integral test. All right, so this is how you use the integral test. Right. Let's keep looking at some examples. This next one is just to illustrate that the integral doesn't have to start at 1. We did see that come out before, but we can look at another example here. What if the series explicitly doesn't start at 1? What if it starts at 3? That's fine. What we'll do is the same process. We'll make a function, 1 over x squared plus 1. We'll show that f is positive. Or, in this case, I'm going to say for x is greater than or equal to 3, because that's the case that I'm interested in, 3 to infinity here. We'll state that f is continuous. There's no places where we're dividing by 0 or anything like that. For x is greater than 3, right? And then if we go through that derivative, that's going to be low d high minus high d low over low squared. Which turns out to be negative 2x over x squared plus 1 squared, which is less than 0 for x is greater than or equal to 3, and that means we can say it's decreasing. F is decreasing. And therefore, the integral test applies. And since the integral test applies, we can now use it. The integral from, I'm just going to start at 3. 3 to infinity of 1 over x squared plus 1 dx. Right, we would make that a proper integral, limit as b approaches infinity of 3 to b, 1 over x squared plus 1 dx. That is resolved to, when we take the antiderivative, arctangent of x from 3 to b, and limit as b approaches infinity of arctangent of b minus arctangent of 3. Right, so there is some place where the tangent is 3, so that exists and is some number. And we already learned from the previous screen that this is pi over 2. So this is resolving to a number. We don't actually have to compute what the number is. We can just say the integral converges. Therefore, the series converges and equals 3 to infinity. 1 over n squared plus 1 also converges. Again, apologies for the handwriting being a little wiggly here. Also converges by the integral test. Okay, so again, this is our longest one, and so we use this only when we need to, but we do sometimes need it. Okay, let's move on to another test. Now, this test is called the p-series test, and it is for a specific form. So just like the integral test and the nth term test are more general, you can do them on a lot of different kinds of forms. Right? The geometric series test had a specific form, just to remind us. It is a series of the form n equals 0 to infinity, a starting value times a common ratio to an n. So if you have a common ratio raised to a power, that's geometric. Right? But this is another form that is specific. If you have 1 over n raised to the p, in other words, not a number raised to the n, but the n raised to a number, and it's in the bottom of a fraction, then it's called a p-series, right? And that means that the p-series would be, it will be 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p plus 1 over 4 to the p. Right? Now, p can be anything here, and we'll see where these ones converge and where they're divergent. But if p happens to be 1 specifically, so when that p constant is a 1, then it's called a harmonic series, where this is just 1 over 1 plus 1 over 2 plus 1 over 3, because that's 3 to the first, plus 1 over 4, and so on. So why is that called the harmonic series? It's actually related to music theory, because if you have anything that's producing musical sound, like a string that's vibrating or a column of air in a wind or a brass instrument, it can vibrate in different modes. So you can, let's say, for example, a guitar string, it can be started, stop your fingers here, and this is where it connects to the guitar, and it can vibrate in this mode, right, which produces a pretty low pitch, a low frequency. But it can also, that same string can be partially vibrating in a mode where it's vibrating in halves like that, which is twice as high frequency. And you can vibrate in thirds and fourths and fifths. And each of those will produce higher frequencies. Those frequencies in music are called harmonics. This is called the fundamental pitch, and these are the harmonics: twice the frequency, 3 times the frequency, 4 times the frequency. And the particular mix of these things gives the instrument its what we call timbre, the quality. So that's why a flute playing a note sounds different than an oboe playing a note, sounds different than a guitar playing a note, because they have a different mix of these frequencies, and our ear hears that differently. Anyway, not necessarily something you need to know for the class, but that's why this is called the harmonic series, when you have a P series where the P is 1, okay? But let's look at what the rules are for a P series. So if you have a P series where you have n equals 1 to infinity of 1 over n raised to any constant, that P can be any constant, okay? Then it will converge if that constant is greater than 1, and it will diverge if that constant is less than 1, okay? So that kind of makes sense, right? If it converges, so if this constant is large, then that means you have something that's getting large faster in the denominator, which in general makes things smaller and will allow things to converge. So large exponents down here converge, smaller exponents diverge. Okay, now I'm not going to go through the proof, but if you're interested, you can prove this theorem using the integral test. So you can read through that if you would like, but we're going to move on to using it. Okay, determine if this series converges or diverges. So as soon as I see this, based on its form, I'm recognizing this is a P series. So I would write that I'm doing a P series. I see that this is a P series. There is a 1 there. So I'm going to identify with that W with a slash is short for with P equals 1. And the rule was that for this to converge, you have to have a P that's greater than 1. So the equal to 1 case is one of the diverging cases. So then you can say, therefore, this series, n equals 1 to infinity, 1 over n diverges by the P series test. All right. So that's it. A lot less writing than the integral test, which is why we would try to use this test if possible before we went to something like an integral test. Okay. Let's do a few more examples. Determine if this series converges or diverges. And of course, with the video here, you're welcome to pause the video, try it on your own, unpause it, see if you've got the problem correct. Okay, I notice that this is in the form 1 over the n being raised to a constant, so that qualifies as a P series, so I'll identify it that. It's a P series with P equals 2, and with P series, large P converges, so therefore we can say, therefore, this series, 1 over n squared, converges by the P series test. Okay, really, it should be simple as that. Let me just make sure I'm not ignoring anything. Oh, simple as that. Okay, since this has not been that long of a video, I'm going to go ahead and finish. There's 3 other examples in here, but you could stop. I think you have enough at this point. These are a little bit more complex examples. Determine if this series converges or not, but it doesn't tell us ahead of time what to use. Right now we've got a few things on our list, right? We've got geometric that we could try. We've got the nth term test for divergence. We've got the integral test. And we've got the P series test. Well, it's not a P series. It's not geometric. So we could try the nth term test, but I'm just thinking, if we were to take the limit as n approaches infinity of the generating rule, that's probably going to go to 0, and that's the inconclusive case, so that's not going to work either. That means we're going to have to use the integral test. All right, so we'll do the integral test. The integral test means that we replace this with a function, 1 over x natural log of x. We have to assert that that is positive, and that's true. This starts at 2. Natural log of 2 is a positive number. Thinking about the natural log curve real quickly, right? This is the point 1, 0. So for anything larger than 1, for example, starting at 2, we're in a region where this is positive. That's positive, that's positive, that's positive. So we can definitely say that this is positive for x greater than or equal to 2, where they say to start. That's true. F is continuous. Also for x's greater than or equal to 2. And I think for the decreasing part, We could go ahead and try let's try a derivative. So I'll use quotient rule again. So that's going to be low x natural log of x times the derivative of high, which is 0, so that goes away, minus the high times the derivative of low. But this one is going to require product rule because we have two things multiplied. So that's first times derivative of the second plus second times derivative of first, which is a 1, over low squared, x ln x squared. So that would be negative, let's see, that cancels to 1, so that's negative 1 minus natural log of x over x natural log of x squared. This denominator is always positive because it's squared, and negative 1 minus a negative x, we know that the natural log of x itself is positive, right, once we get above 1, right? So that'll be positive, so we'll have a negative 1 minus more, so it's going to be negative on the top. That means this is less than 0, and therefore f is decreasing. So we've shown the third condition is true, therefore the integral test applies. And we can now use the integral test. So to use the integral test, we'll do an integral from, let's see, we're going to start at 2, from 2 to infinity of the integral 1 over x natural log of x dx. We'll make it a proper integral, limit as b approaches infinity, integral from 2 to b of 1 over x natural log of x. And then I'm thinking maybe we should do, u substitution maybe with this log, because the derivative of natural log is 1 over x. So let's do a u substitution with natural log of x is that. That means the derivative will be 1 over x. So the du is 1 over x dx. So this becomes, let's actually do the whole the indefinite integral, x natural log of x dx. We'll convert to 1 over u, and this 1 over x dx becomes the du. So that is, let's see, natural log of u, which is then therefore the natural log of the natural log of x. Okay, that's the antiderivative. So we're going to take the limit as b approaches infinity of the natural log of x from 2 to b. So that's going to be limit as b approaches infinity of natural log of b, and then minus the natural log of 2. This is definitely a number, but natural log of b is an infinity, and the natural log of infinity is an infinity, which means that this integral is diverging. The integral diverges, and therefore we can say the series n equals 2 to infinity of 1 over n natural log of n diverges by the integral test. Okay, so that was quite a bit of work because, yeah, integral test is the worst one while writing. All right, let's do two other quick examples. Determine if this series converges or diverges. All right, so it doesn't necessarily look like a p-series yet, but it is, because we can rewrite this as a series from 1 to infinity of 1 over n to the 1/2 power. That is the n to a constant, so that is a p-series. With p equals 1/2, which means this diverges. Therefore, right, with p-series, you need large p in the denominator to converge. That series diverges by the p-series test. Okay, so that was easier. We could recognize that that was one of the forms. All right, let's do one more here, and then this is the last example, I think. Oh, there's more here too. And we'll keep going. And of course, you can always pause the video if this is getting too long. Determine if the series converges or diverges. This is not a p-series. It's not geometric. It's not going to work with the nth term test for divergence, so we're going to have to do integral test. So let's do that real quick. F of x is 1 over 3x plus 1. So, I think we can say f is positive. for x is greater than or equal to 1. We can say f is continuous for x is greater than or equal to 1. Yep. And we can do the derivative. So low d high minus high d low over low squared. That simplifies to negative 3 over 3x plus 1 squared. The bottom is positive because of the square. The top is always negative, so that is less than 0. So this is decreasing. Integral test applies. And now we'll use it. So we make an integral from 1 to infinity of 1 over 3x plus 1. Make it proper. Limit as b approaches infinity of 1 to b of 1 over 3x plus 1. A little u substitution, 3x plus 1, so du is 3dx. So this becomes, for the definite integral, 1 over 3x plus 1 dx is the same as 1 over u. But then the dx gets replaced with 1/3 du. So that's 1/3 natural log of the u, which is 3x plus 1. So now we've got limit as b approaches infinity of 1/3 natural log of 3x plus 1 from 1 to b. And so we've got 1/3 natural log of 3x plus, or 3b, sorry, plus 1. And then minus 1/3 natural log of 3 times 1 plus 1. And this one requires the limit. So as b goes to infinity, this goes to infinity, which means the natural log goes to infinity. That means that the integral is diverging. The integral diverges, and therefore the series also diverges. N equals 1, 1 over 3n plus 1 also diverges by the integral test. Okay, let's see. Got a couple other examples here. Are they worth doing? I think. Oh, we're going to skip that one, I think. Yeah, I think for this, I'll put these last two examples in a separate video. If you're interested, they're more complicated and they're not really kind of the standard case for the homework. So we'll end this video here and I'll do a separate one covering these last two examples. All right, so that should be it.